Okay, the exam results. I gave partial credit on some of the problems. So some of the problems that weren't multiple choice, you had to put in a number, and I kind of had to guess, how far you got with the problem. I mean, some of you, if you were off by a factor of 2 or something, I could see that you were headed in the right direction. Everyone passed. Yes. Okay, everyone passed. The median score was 80, but the average was only 76. So when these two things are not equal, that means you have a skewed distribution. It's not even. They were more clumped up in the higher end, and then some of the lower scores lowered the average, but there were not too many of those. And the highest score was about 97. I think we had some 95, 97 scores. Yeah. So again, if you're interested in finding out about the questions that you didn't get right on the exam, we can do that individually. There won't be a final exam, so this material is finished for the semester, basically. Okay, so here we are. Week 7. We're going to do magnetoelectronics, and then you're going to build a magnetometer in the lab this week. And then after that we'll have one more analog week, and that's optoelectronics next week. And then after that we'll go into digital electronics. We'll have both Monday and Wednesday lectures next week. Okay, so that's some digital basics and logic networks and so on. And then we'll have a week after that pulsed ICs, and then we'll have an exam on the material since the last exam. And then we'll start working on the final project. That's a problem because most of you can't build anything. We can't get the parts to you. There are just a lot of logistical problems with that. Anyway, we're going to have some sort of final project. And then the last thing, instead of a final exam, we're going to have you're going to turn in a PowerPoint poster, basically. You're going to make a poster out of one of your experiments. Okay, and that's just one page. Any questions on that? The future?
Real quick, Professor, on terms of the midterm, what's the letter grade scale in terms of grades? Like, what is considered passing? What is considered what grade?
Yeah, everybody's passed. I haven't. I worked that out once, and I'm not satisfied with it. So I'm gonna look at that again. So, but I'll let you know. Okay. I think basically 80 and up is 80 would be, if you had 80 to 85, something like a B+, and then it goes on from there. Yeah, I know you want to know what the breakdown is in terms of, are you on the borderline between B and B+ or whatever, but it really doesn't matter because it's going to be the final, the final grade is really going to determine it. But I'd say if you did pretty well, you're at least a B+. If you did near the median. Okay. Okay, magnetism and electronics. There's a lot of magnetism that we use. That's one of my specialties in physics, is using the magnetic properties of materials, and especially the magnetic property of single electrons. Okay, so I'm going to look at the power grid. I mean, you think, well, okay, the power grid, well, that's not electronics, that's electricity. But where would we be without electrons moving around, and how are they going to move around? If we had a big blackout for a week, what would you do? You wouldn't have your phone. You wouldn't have any sort of communication with people. So it's very important, the power grid. Transformers, going to go over the physics of transformers. Faraday's law of induction, Ampere's law. Some of these things you've already had, you should have had in physics too. Then we'll look at magnetic solenoid. Another use for transformers is impedance matching. Impedance matching, we'll go over that. And then we'll look at a little bit, just one slide on the experiment this week. This is a short lecture today. I only have, I think, 16 slides. Okay, the power grid, very interesting. If we look at the US power grid, this is an older number, but it's probably several 100,000 miles of wire in the grid. That's just getting to power stations, not even counting what goes to your apartments or houses. Here's a map, and you can see roughly the lines of different power lines and the voltages. The colors represent the different voltages. You can see 100 kilovolts up to 500 kilovolts, which is a half of a megavolt. They're even higher than that. So let's take a look at a couple videos to give you a sense of what it's like. So let me make sure I can do this. And I'll have to stop sharing. And here we go.
When we talk about the U.S. electric grid, we're referring to the large high voltage power lines used to deliver bulk power, as well as the hardware that links them together.
Say something if you can't hear this.
Miles of transmission lines that move electricity from power plants to cities and towns, and from one part of the system to another. The grid's designed so that if demand goes up in one location, or a major transmission line or other electrical infrastructure goes down due to weather, a technical malfunction, or even a terrorist attack, power can be rerouted to prevent blackouts. But it's not always effective, as the big 2003 blackout in the Eastern interconnection demonstrated when 50 million people lost power. Is it just one big grid? Not quite. Actually, it's three grids, also called interconnections. The Western, the Eastern, and the Texas interconnection. While plenty of power transfer goes on within each of the three interconnections, there's not much ability to move power between them. In a pinch, California, for instance, could rescue New York. On this map of the grid, the blue lines are high voltage direct current lines able to carry bulk power across long distances. In the West, for example, they help supply Southern California with electricity from the Pacific Northwest in the summer, and power flows reverse in the winter. DC power has to go through conversion stations before transferring to AC, alternating current lines. High-capacity AC lines, the red and dark orange lines on the map, link areas like the Midwest, the Eastern Seaboard, and the Southern U.S. One challenge for today's grid, the highest transmission lines don't reach some of the newer renewable sources coming online, like wind and solar, because they often are in remote locations. What are substations for? They're essential. When power leaves a generating plant, it usually goes to a step-up substation to increase the voltage before the electricity can ride the high-voltage transmission lines. But before that power can get to end users, it must go through another substation that brings the voltage back down again. Some industrial facilities can handle this level, but for homes and offices, the electricity must pass through a separate distribution system with its own substations. That brings the voltage down even further. It's reduced a final time on those transformers you see on electrical poles, delivering the 120 to 240 volts you get from a wall socket. What causes blackouts and brownouts? The system has redundancy built into it, but if demand increases too quickly and there aren't enough power plants online to ramp up production, grid operators usually order rolling blackouts until the system gets back in balance. Also, if too many high-capacity transmission lines or transmission substations go down at once, for whatever reason, the system or parts of it could be overwhelmed and fail. That's the short answer.
Homeowners are raving about Lethal, the proven solution that ends gutter cleaning forever.
If it keeps out shingle grit and pine needles, it'll keep out everything.
It's protected my home. I love it. Get your free estimate now.
Okay.
Every morning at 4:30, you hear the cook hop on the floor.
Okay,
It's
what are we doing here?
hard times in the middle, my love. Hard
Okay.
times in the middle. Every morning right at 6. Don't that old bell ring?
You should be able to skip the ad if you press skip.
Yeah, I don't see skip here though.
It's like right to the right of your cursor. Like,
Oh, okay. It's hidden. It's hidden behind something. Yeah. Okay. Thank
On
you.
This week's Fully Charged, I've come somewhere
Yeah.
I really can't tell you about. This episode of Fully Charged comes from National Grid Control Centre, which is somewhere in England. And I've come along here to find out more about the grid, because the more I learn about things like renewable energy and electric vehicles, the more the grid becomes the focal point of that discussion. How is the grid going to develop? How is it going to be able to utilize new sources of power? So I thought I'd come along here and ask some people who really know what they're talking about. So we're in the National Grid switching room, and I want to know what the National Grid is. It's just loads of wires, isn't it?
Well, here is the Electricity National Control Centre. So from this room, we control all the electricity generation and demand.
Yeah.
That's what makes this room very unique.
Right. So in this room, then, you control where the electricity comes from, and then
Yes,
how it gets to our houses.
exactly. So there's two functions here. One is the transmission function, where we look at the physical transmission network and the routing of power. And then there's the energy side, where we're controlling power stations' output and monitoring demand and making sure that balance is exactly level, because we have to manage this thing called system frequency,
Right.
which is a function of the balance between generation and supply.
Right. So Nigel, for the lay person, I mean, I can understand that bit because that's a map.
Yeah.
The overall amount we're generating at the
Yes.
top is at the top
Yes.
number. What we're using below that.
And then the transfers with the plus and minuses of all the inputs and outputs from Netherlands, France, and Northern Ireland.
I see. So we're sending some to Northern Ireland. We're getting some from the Netherlands,
Exactly.
some from France.
The rest of the diagram here is, as you see, this is England, Wales, and Scotland on its side. On its side, with England, Wales, the main transmission circuits, the blue, which is
Yeah.
400 kV, the red, which is 275 kV, and all the yellow lines you're seeing there, they're circuits out of service. So that's maintenance activity.
Right.
We have 340 odd substations.
Right.
And you see them all in the squares,
Yeah.
and they're hubbing points. There's nobody manned in these substations,
Right.
all controlled from here.
And then underneath those, the generation mix, which is fascinating to watch those.
Yes, that changes day on day, of course. Also, quality different.
Okay, take a look at this. This is 8 years old. Coal produces most of their electricity. Gas is second. Nuclear is third. Let me see if I can get a better picture of this.
Trading patterns and different prices.
What is the sort of peak of peak?
We go back a little bit.
Quality different trade.
It's someplace they had listed the percentages. I don't see that right now. But
Trading patterns and different prices.
What is the sort of peak of peak demand?
maybe I'll show that again.
Most that we use.
Yeah, well, we had the peak
They're to the right of the bars, a little bit before where you stopped.
at 60 gigawatts, 60,000
Okay.
megawatts.
Let's go back there. There we go. Okay, so coal is 45%, gas is 31%, nuclear 20%. Look how much wind and water. Water comes from dams and turbines, and then they have wind. I think wind's gone up a lot in the last 8 years. I don't think water has very much. I used to teach a course here on energy and the environment, and we looked at ways and how to get rid of the first two, coal and gas and oil, of course. And one of the issues is you want to have more wind, more solar, more water power, more hydrothermal. The problem is those are still very small amounts of electricity that we get from those. I mean, we're still getting huge amounts. I mean, here you have 3/4 of all the electricity comes from coal and gas. Oh. I think they've probably gone over a lot more to gas, and coal is probably these percentages have probably reversed in the last 8 years.
Which is fascinating to watch those numbers.
Yes, and that changes day on day, of course, according to different trading patterns and different prices.
What is the sort of peak of peak demand, really? What's the most that we use?
Yeah, well, we had the peak of peak in February this year.
Right.
So our peak of peak is about 60 gigawatts, 60,000 megawatts.
Right.
So today, for example, you can see on the wall here, our demand at the moment is 42.9,
Right.
which is a typical summertime sort of plateau period.
Right. So it isn't a flat line.
No, I wish it was.
Quite a violent change. I mean, I was amazed at how big the changes were.
Yes, and especially in the winter time, the sort of evening peak demand, the demand comes on really hard when darkness coincides with the 5:30 time when people come home from work,
Right.
and you get a massive peak there, and then it drops down in the evening.
Right.
And we've all heard about what happens when Coronation Street finishes or EastEnders finishes,
Yeah.
where people turn on the kettles and stuff. We
Right.
get big power surges.
Right. But also, 10 years ago, you had coal, nuclear, gas, and the story, really. That was it, wasn't it? And now you've got a plethora of other inputs.
Yes, our world is changing massively, and
Right.
you can see today our wind is really down.
Right.
But if you pass me the
Oh, yeah.
the wind forecast, we can see here the wind forecast is really picking up. Tomorrow we're getting up to 4.5 gigawatts of wind,
Right.
which will pose us some operational problems here. And depending on where that wind is, then maybe there's some actions we'll have to take.
Right.
But we'll very carefully study that, and we'll overlay the generation scenarios
Right.
onto the transmission network, and we flesh out any problems that we may see tomorrow,
Right.
and we'll take action accordingly.
So when that happens, at the moment, can you then reduce the call on carbon-based generating systems? I mean, can you turn
Yes,
down
we
the
do.
coal a bit?
We do.
Right.
We do it in cost order. So all the power stations submit us costs
Right.
in advance, and then we'll call off some of those costs in cost order, the most expensive first,
Right.
in order to meet that balance.
Right.
But there are other issues as well. For example, integration with Europe is an issue. So we're becoming more connected to Europe. We're going to have more wind, we're going to have more microgeneration and more solar. And as far as we're concerned here, it's all about data and forecastability,
Right.
and the ability to model everything that may or may not happen on the network. Do more analysis here to make sure that the transmission system is robust, that we can transmit power both north to south, which is predominantly the case today. But in the future, the power flows are going to be south to north, east to west,
Yeah.
south to north, anyway, which way.
Yeah.
That's the big challenge for us.
I mean, one of the obvious things that we really need is a way of storing that energy.
Yeah,
because-
storage would be a massive thing for us,
Yeah.
especially overnight in Scotland, for example, when the demand dies away, there's a surplus of renewable, good, cheap, green generation,
Right.
and where the transmission system is unable to ship that power out,
Yeah.
and we would otherwise have to curtail energy, then a storage solution just what we need as a
Yeah,
country.
yeah.
But of course, the scale we need it in is quite
It's
a
big.
challenge. It's
Yeah.
big, and
Yeah.
there's nothing of scale
Right.
to face the challenge we've got.
Anyway, let's. I wanted to stop there, but one of the problems with it with the grids is when some power goes down or up, and suppose you needed more power all of a sudden. Well, you can't just turn on, a gigawatt power generating plant. It takes time to do that. So that's one of the problems. That's why he was talking about being able to store energy in something where you can turn it on and off fairly quickly. I mean, there are things like in a dam, you have big turbines that when the water falls down, it generates electricity in the generators, but then you can reverse. Then when you have extra power coming from a power plant, you can reverse and make those generators into motors, and you can pump water back up into the dam. And that's something you can do fairly quickly, as opposed to you know, a nuclear plant or something like that where you can't change it very quickly. Let's see. Can you see the PowerPoint slides right now?
we
No,
still
it's
see
still on
video.
the video.
Okay, so let's go. Let's go here. Okay, let's share again. Sharing. Okay, where is sharing here? Where is my sharing? Okay. Not up at the top, not up at the bottom. Ah, there it is. Green, of course. Yeah, okay. I have to go back and forth a couple times. Excuse me. Okay, here we go. Okay, in the you can see the slide now?
Yep.
Yeah, great. Okay. So we've seen this before. You have a generating station, you step up to some very high voltage, you know, almost 1,000,000 volts, and then you go to these other substations and other places with transformers. Something I'd like to point out here in the bottom is here's in any fossil fuel burning plant or nuclear plant, you generate electricity by heating some liquid, and then that liquid goes into a gas, and that gas expands, and that gas rotates turbines, and those turbines are connected to a generator, and that generates electricity. Well, because of the Carnot efficiency, when you're turning this heat into electricity, the efficiency is it's almost never more than about 40%. So whatever heat you're producing down here, more than half of it has to be sent away up into the atmosphere. Otherwise, your plant will burn up. So that's why you see some of these cooling towers. This shape is a hyperbola. So it's a hyperbolic, basically a flue or a chimney that takes the heat away and puts it in the atmosphere. But these things are just not very efficient. It's because you have a certain temperature at which it starts, and then a temperature at which the gases leave, and that difference in temperature, when you put it into the Carnot model, you're never going to get more than about 40% out of it. If you could make them much hotter, yeah, then to start with, then you could get a larger Carnot efficiency. But these things are just not very efficient. Questions?
I have a semi-related question.
Yeah.
Like I'm looking at the map of the U.S. right now, and where they use different voltages. I understand like why they use different voltages for like the long-term, like the long distance power transmission. But why is it seeming that there's just random voltages for different areas of the country? Like the middle section of the South is using 161 kilovolts, but Texas is using like 138. Does that have any real relation?
Yeah, I imagine it just has to do with how much how much power they have to give to a certain place, and what distance they have to go. Both, you know, those two things. Yeah.
All right, thank you.
Yeah. I don't have any more information than that. Okay. Did you hear about DC? Well, one of the videos, the first video, talked about DC, but this whole time we've talked about how AC is much better, that you need much smaller wires because you can have higher voltage. So that's why you go to AC. For transmitting voltages near 1,000,000 volts, you go back to DC, okay? And there's a reason for that. There's something called a skin effect. You know that AC, when a current flows, current in a wire makes a magnetic field. And it turns out that what happens there is there's something called the skin effect, where depending on the frequency and the current, that most of the current is only flowing in the outer edge of the wire, that there's almost no current flowing in the inside on AC. So what that means is, instead of a wire having this, you know, large diameter here, you have a wire that's much smaller cross-sectional area. So it would have much less resistance. Sorry, it would have much more resistance. So AC. So then when you don't have AC, when you have DC, you don't have any magnetic field that's confining the current. So then in DC, you can utilize this whole area of the wire, the whole cross-sectional area, for conducting current. So it has no skin effect. One of the problems with AC is AC has a phase. So when one power generating plant has a different phase than another, you know, you just can't add it in. What if it's out of phase? You add some AC signal that's out of phase with the other one, it's going to, you know, reduce it rather than add to it. And then there's some other possibilities here. Anyway, so when you're near a megavolt, they go back to DC, back to DC current. Okay, but let's go back to AC now, because we're going to look at transformers and the physics of transformers. So in a transformer, you can change the voltage up or you can change the voltage down. Here's something you might find in one of your audio amplifiers, or you know, in some other piece of electronics. You might have something like this where you need high voltages. Or here's something where you have this is a transformer. Okay, you can see the person standing down here. These things are huge, and you have to have a way to take the heat out, and all this stuff, this big box on the side and this container up here, are for taking heat out of the transformer. And notice something at the top here. I thought this was really cool, that here's an insulator here going up here, and so the wire is going to be hooked onto this whole transformer is way up here, because you don't want the voltage to arc to something. So you have this very long insulator that keeps it from, you know, arcing onto this thing. Okay, so transformer is simply two coils of wire in the simplest sense, and two coils of wire that have a magnetic material between them, because they act by magnetism. Even one like this, it's on a pole, maybe in some neighborhoods where the electricity doesn't go through wires above ground. You know, if it goes above ground, then they'll have things like this in the neighborhood that change 4,000 volts down to 120 volts or 240 volts. But look at transformers. sometimes I ask students, what do they think what the efficiency is? I probably should have shown this. The efficiency of a transformer is 99.5% in modern transformers. Using a donut like this, you get a little bit higher efficiency with it, but still in other types, you still get a pretty high efficiency. So the energy loss in the US due to heating in transformers is only about 7%, or, you know, quite small, quite small. I mean, you compare that to the efficiency of a power generating station, which is only about 40%. This is not very much. Okay, transformer, two wire coils around an iron core. So we usually have a primary coil and a secondary coil, and then here's this iron core. It's passive. It's a passive component, meaning the power is a constant. Or one aspect of being passive is you're not putting any other energy into it, or you're not taking much out. So the power going in has to be the power going out. So if you want to make the voltage go up by a factor of 1.6, the current has to go down by a factor of 1.6. Okay. So how does this work? Okay. We know what magnetic flux is. It can be produced by a current. You know, when you have a battery like this and you put it around a coil in a nail, you know, you can attract metal objects because the coil and the current have produced a magnetic field in the iron or in the steel of that. And one thing about it, why these things are so efficient is because the magnetic flux. So you have a coil here that has a current in it, and it produces a magnetic field, magnetic flux inside of this. And magnetic flux is trapped in this square donut. And so almost none of it gets out. And so all of the flux you made here is going to be felt over here in the secondary one. So here's an example of a transformer where, you know, if you want to plug something, you want to charge your phone or something with 5 volts and you have 120 volts plugged into the wall, well, you use a transformer to step down the voltage. Okay, so let's look at the physics of transformers. They operate to amplify either AC voltage or current, but of course you can't do both at the same time. And I look at it as a 3-step process. First, you convert AC current into flux here. So the current produces a magnetic flux here. The flux is transferred over to this one, and then you reverse it, that the flux here is transferred back into current into this one. So current to flux in the primary, transfer of flux to current in the secondary, just that simple. Let's look at one of these, how a transformer works. Look at the first 3 minutes of it. Okay, share.
Hello, everyone. I am asking for your help in us taking back the United States Senate by chipping in right now.
Okay.
Transformers are capable of receiving AC power at one voltage and delivering it at another voltage. In this way, they help achieve better transmission efficiency while transferring the power over.
Yes.
Right.
In this video, we will go through the working and construction of a 3-phase transformer by starting from its simplest form. The basic working principle of a transformer is simple: electromagnetic induction. According to this principle, a varying magnetic flux associated with a loop will induce an electromotive force across it. Such a fluctuating magnetic field can easily be produced.
Let me stop there just for a second. Back up just a hair. Okay, so to get a current, right, you have to have a voltage basically driving it. If you don't have a potential difference, you're not going to get any current. So you have to have a voltage produced. Okay, this is one of the reasons why a transformer doesn't work with DC. And we'll get to that in a little bit. But just remember that you have an electromotive force is basically a voltage. It's a force that's going to cause the current, going to drive the current.
Field can easily be produced by a coil and an alternating EMF system. A current carrying conductor produces a magnetic field around it. The magnetic field produced by a coil will be as shown in the figure. With the fluctuating nature of the alternating current, the magnetic field associated with the coil will also fluctuate. This magnetic flux can be effectively linked to a secondary winding with the help of a core made up of ferromagnetic material. This fluctuating magnetic field will induce an EMF in the secondary coils due to electromagnetic induction. Since the turns are arranged in a series, the net EMF induced across the winding will be the sum of the individual EMFs induced in each turn.
Let me point out something here. Okay, so what will happen if you don't have AC? What happens if you have DC current flowing in this coil? So that you get some current in here, you get a magnetic field and magnetic flux here. The magnetic flux goes over to here, and there's a magnetic flux in here. The problem is it will not produce an EMF of voltage. So it will not produce a current in the secondary if it's DC. If you have a static magnetic field in here produced by a DC current here, then you won't get any voltage in this to drive a current in this coil.
Since the same magnetic flux is passing through the primary and secondary coils, the EMF per turn for both the primary and secondary coils will be the same. The EMF per turn for the primary coil is related to the applied input voltage as shown. As a result, the induced EMF at the secondary coil is expressed as follows. This simply means that with fewer turns in the secondary than in primary, one can lower the voltage. For the reverse case, one can increase the voltage. But since energy is conserved, the primary and secondary currents have to obey the following relationship. Three-phase transformers use three such single-phase transformers, but with a slightly different coil configuration. Here, the primary and secondary coils sit concentrically. Two more such windings are employed in a three-phase transformer. Transformers with high power ratings generally employ a special kind of winding, known as a disc-type winding, where separate disc windings are connected in series through outer and inner crossovers. The low voltage windings are connected in a delta configuration, and the high voltage windings are connected in a star configuration.
Well, I didn't want to get into the details of this particular thing, but maybe we can go to the end of it. Yeah, here. Tesla invented three-phase power, or multi-phase power, it's called. So here you have what's called three-phase.
So usually the transformer is immersed in a cooling oil to dissipate the heat. The oil dissipates the heat via natural convection. Oil in the tank will expand as it absorbs the heat. A conservator tank helps to accommodate for this volume change. To know more on different types of transformer cores and windings, please check out our other videos. Thank you.
Okay. Okay. Okay, so in physics, how do you convert a current in a coil into magnetic field? Okay, we're going to use Faraday's law of induction. Okay, you have a magnet going into a coil of wire, and you can see that it's producing a voltage as it goes in, and when it comes out, it produces a negative voltage. Okay, so it depends on whether it's going in, whether if the field is increasing in the magnet or if it's decreasing in the magnet, gives you a plus voltage or a minus voltage. Okay, so you get this induced EMF, or basically a voltage, and it's created by this magnetic flux changing in time. So we can say the EMF, the voltage, is negative derivative of what we call the flux. Time dependent. The flux we're going to say is just magnetic field times area. But it depends on these are both vectors. So if the magnetic field and the area vector are parallel, then it's just B times A. So it depends on the angle between them, since it's a dot product over here. Okay, so let's compute the voltage in a wire from a coil from a changing magnetic field. So the EMF is minus d phi dt for one turn. If we have n turns, then we just multiply that by n, and we put in the flux here, BA cosine theta. And then we're going to say theta is a constant, so the voltage produced is just minus the number of turns times the area times the rate of change of the magnetic field. Okay. Okay, so here's something to think about. Okay, it looks like this magnet is just going in effortlessly, right? Okay, you're just putting this magnet in and out, but it's producing a voltage. How can you produce a voltage and are you getting something for nothing? If you're putting no energy in to move this magnet in, how do you get a voltage out of it? Think about that. Can you get something for nothing?
No, moving the magnet takes work, right?
Well, should it? I mean, suppose this magnet were on a string as a pendulum, and you just let it swing in and out for a while, and there was no friction on the string.
Well, there's also going to be a force acting on the magnet, right?
Aha, that's it. Yeah. Okay, where does the energy come from to push the magnet in? If you're going to get something out, you're going to have to put some energy in. Okay, it turns out that Lenz's law, there's an induced current in a closed loop of wire that generates a magnetic field that opposes the change that produced it. So if you're trying to push this magnet in, you're increasing the magnetic field. That is going to produce a current, and that current is going to produce a magnetic field that pushes against the magnet, So if instead of just hooking this thing to a voltmeter, if you hooked it to a resistor or something where it dissipated energy, then you'd have to push this thing in. It would take some energy to push this thing in, and the energy would go into heating up the resistor. Okay, it takes energy to force the magnet in against the opposing magnetic field. So here's basically what his law is. So if the magnetic field is increasing, it's going to produce a current in the opposite direction to oppose that increase. So yeah, it's going to take you energy to push it in if it's going to produce energy. Of course, if the coil is not hooked to anything, then it doesn't take any energy to put in, to push this thing in. So this is kind of a subset of Le Chatelier's principle that in general, any change in status quo prompts an opposing reaction in the responding system. I mean, I think this applies more to chemistry, but when you're trying to change something, it's basically opposing it. Any questions? Shall we move on? Okay, so let's take this example of computing the magnetic field in a solenoid. A solenoid is a coil of wire. It can have an air core, can have a iron core, can be any number of things. So how do you calculate the magnetic field inside of this solenoid? This is a cross section of the solenoid. So these are wires going, say, with current going into the board, and these are coming out of the board or slide here. Okay, so we're going to define an area here. We're going to define a path that encloses a number of turns of wire. We use Ampere's law. Ampere's law says that if you have a current, you're going to generate a magnetic field. So we're going to compute the magnetic field by going around from A to B to C to D and back to A again, around that loop. We can make a couple assumptions. One is that the magnetic field is constant in here. The second thing is the magnetic field right on the outside of the solenoid. If the solenoid is long enough, the field will be constant inside, and it will be zero right outside of it, if it's long enough. If it's long in comparison to its diameter. So if you go from A to B, the magnetic field, say, points up, and the direction A to B also points up, so they're parallel, so it's just B dot DL. They're in the same direction. B to C, little dl, this line here, this L here, is perpendicular to any field. And outside of here, along from C to D, B is 0. And then from D to A, it's perpendicular again. So by the time you put all these things together, this is the only thing that comes out of it, is B times the length. Okay. So B times the length is equal to the number of turns times the permeability, mu0 times the current. So when you divide by L, it's the number of turns per length. Okay, turns per length. Because you might figure, well, if I want a bigger magnetic field, I'm just going to make this thing twice as long. Okay. By making it twice as long, the field doesn't change as long as the number of turns per length, turns per centimeter, turns per meter doesn't change. It's not going to change the magnetic field. So if you make this thing, the solenoid, twice as long, you're going to get the same magnetic field, but it's over twice the volume. So that's what you gain. It's just over a bigger volume, but you don't get any higher higher magnetic field. So here's a question: how would you get a higher magnetic field in a solenoid like this? How would you make the magnetic coil differently to get a higher magnetic field?
Wind it tighter.
What?
Wind it tighter.
Well, right here, I guess you could. If you had smaller diameter wires, you could pack more in there. That's one way, right?
You could increase the number of turns.
Where?
In the wire overall.
Yeah, exactly. That's exactly what you do. You'd have like 2 layers of turns. So you'd add another layer of turns out here. In fact, you can put, 10 or 20 layers of turns out here. So then you're having the same length along the solenoid, but that many number of turns if you just doubled or tripled the number of layers of wire that you had. So when you're making a coil, you just wind a coil like this. Then you start winding it back on top of it and then back on top of it again, and you get the higher magnetic field that way. Okay, very simple. B this time is mu0 times I times N. So I would be in amps, N would be the number of turns per meter, and B would be Tesla. Okay, because you can see that up here, mu0 is Tesla meters per amp. So if you multiply by current, you get rid of amps. If you divide by the length, meters, you get rid of meters, and then you're just left with T for Tesla. Tesla. It's in SI units. Okay, so summary, you're converting in a transformer, current's giving you a flux. The flux is trapped. I mean, in a sense, the flux is trapped almost like light is in an optical fiber. You've all seen optical fibers. That sometimes you see these things on somebody's shelf where the light comes right out of the ends of the fiber and it's kind of trapped in there. Well, it's the same sort of thing, but instead of the electric field of the light, here we have the magnetic field of the flux. Okay, so now we have that. We can calculate what sort of voltage we're going to get when we put a voltage in here and get a voltage out. So we assume that the flux the magnetic field is B proportional to I. Magnetic flux is B times the area. And the voltage produced, now, so we're going to use this formula and this formula and put them together. We have the same flux, and the flux d phi dt is the same. So for the primary, it's the number of turns of the primary. For the secondary, it's the number of turns of the secondary. And this just gives you the ratio of voltages is just the ratio of turns. So it looks like a gain. So when we write our gain, we can just say it's the ratio of the turn. It's a turns ratio. In fact, that's a terminology that you would use, is what's the turns ratio of this transformer. Just the number of secondary turns divided by the number of primary. Does it depend on the number of turns per unit length? Good question, huh? Does it depend on the number of turns per unit length?
I think yes in general, because we assumed L is fixed here, but if it wasn't, it might.
Yeah, it's a good question. Okay, so you can look at the current. If you say the flux in the primary and the secondary is just, you put in what B times A is. B times A is the flux. This is B and this is A. So this is the primary and this is the secondary. So you get the ratio. The current ratio is the inverse of this turns ratio that you got for the voltage. It's the inverse, which you'd expect. The current, if the voltage goes up, the current goes down, so that the power is conserved because the flux is the same. Flux is the same. Any questions? Okay. Next, we're going to see how we can use this in something else. Okay, we did all this just to find out it's a turns ratio, right? There's something very important in any circuit of electronics when you're trying to get power out of something. You have to match the impedances, and you can do that with a transformer. Okay. Suppose you have a 100-watt amplifier. I don't know, your guitar amplifier or radio station or whatever, and you want to put that into a speaker. Well, the speakers have some resistance. So you're taking a circuit that has some sort of impedance, and you're trying to attach it to a speaker. So the amplifier and the speaker have different impedances. Okay, so you have to do something about that. So here's an example. Okay, here's a circuit that's part of an amplifier, right? You have a transistor here that can turn on and off. When you turn the transistor on, its resistance is near 0. So this point here goes to near 0 volts. So you don't get anything out here. When the transistor is off, its resistance is very high. So then you just have this resistor and this resistor in series. Okay. So if you have 100 volts here and you have this sort of resistor here, then just from a voltage divider, even though you started with 100 volts here with this 8 ohm speaker, you're only going to get 7 volts out. So that means you start off with 120, you start off with a 20 watt amplifier, and you're only going to get 6 watts to the speaker. Okay. Okay, so that's not working very well. I might mention that speakers getting energy from the speaker into the air molecules, that's very small too. That's only like 1%. So that means you'd be getting milliwatts of energy into the air to transport it to your ear. Okay, so how do you fix this? How do you fix this? With a transformer. It's called an impedance matching transformer. Like if you had 500 ohms in your amplifier and your 8 ohm speaker, then you can figure out what turns ratio you need for that. Okay? And you do that the following way. Okay, so we're going to talk about impedance, which is basically resistance, just voltage divided by current. So you have the secondary and primary, and then you get the impedance ratio in terms of the number of turns, the turns ratio, and it turns out that it's the square of the turns ratio. Okay, so when you're trying to match, so if you know what the impedance of your source is, or your source here, and you know the impedance of your speaker, the secondary here, then you can figure out what sort of transformer you need, what sort of turns ratio you need. So here's an example. You have your 50 ohm function generator in an 8 ohm speaker, and you need a voltage divider. And if you have 50 ohms and 8 ohms, then you have a voltage divider here. Let me point out something very, very good in electronics. See, this is a function generator over here. So you're trying to put out a sine wave. It has a built-in impedance, right? Often to solve a problem, all you have to do is redraw it in a different way. Okay? So I took this resistor and I pulled it out in my drawing and put it up here. So as soon as you see this, you say, aha, that's a voltage divider. But I couldn't see that very well over on the left. So often you want to redraw something. And it begs the answer. Sometimes it begs the answer just when you get the drawing right. Okay, so in this case, you're only going to get 14% of the voltage to the speaker. But now you know these two resistances, Z sub P, the primary, and Z sub S, the secondary. You can take the square root of that ratio, and then it tells you need a turns ratio of an impedance matching transformer to be 2.5. So if you're going to have 100 turns on the secondary, you need 250 turns on the primary. And all amplifiers have this, because almost all amplifiers you would buy are made for 8 ohm speakers, because 8 ohms is the general impedance that they built into speakers. Okay. By the way, a speaker has just a coil of wire. A speaker has a coil of wire and a piece of metal in it, and as the magnetic field in the coil changes, it's changing a piece of metal that's near this coil, and that moves the cone back and forth. So that's how normal woofers and most speakers work, is just by a magnetic field and a coil. They're also piezo speakers that work at higher frequencies. Let's see. Any questions about this impedance matching?
I have a quick question. Could you explain the percentages one more time, please?
Percentages. Okay. Yeah, this is we've used a voltage divider. I don't know how many times in different ways, but often when you see this, so if I hooked a voltmeter in, across the speaker here, right? I mean, it's just like the speaker looks like a resistor, and the amplifier has a resistor in it. So these two resistors, you have a voltage divider. So if this thing's going to put out a certain voltage, whatever it is, then the voltage you're going to get out across this effective resistor here is going to be a fraction of the whole thing. And that fraction is just the ratio, using the voltage divider formula, just the ratio of the resistance of this one divided by the sum of the resistances here. So 8 over 58 gives you 14% of the voltage.
All right, thank you.
Yeah.
I have a question.
Sure.
So why are we, so if 100% of the voltage, the current is going to be less than the source though, right?
Yeah.
And so if we're interested in like the power output of the speaker, isn't that still going to be less?
Okay. Well, okay. So if you have a certain voltage on the speaker, then you can calculate how much power you get out of the speaker by voltage squared divided by R. So here, whatever this voltage is. So it's about 7 volts, I guess. Is that right? It's 1.7. So yeah, the amount of power you're going to get out of this is much smaller because of the smaller resistance. Yeah.
All right. I thought, so I was thinking of, I guess, so in both cases, the current to the speaker is going to be the same, or no?
Well, the current is going to depend upon the total resistance here and the voltage that this thing can produce. Yeah.
All right.
And in the function generator, we know that it goes up to about what? Plus or minus 20 volts, roughly. Yeah, so this impedance matching transformer is one of it's that small transformer that I showed you a picture of that you can find in just about every amplifier. Any other questions? Just about done here. Okay, the lecture today was fairly short, and the experiment is fairly short this weekend. Okay, so we're going to make a magnetometer, and we're going to do that with a 741 op amp and 1 resistor, 1 capacitor, and a coil of wire. Well, of course, you need an oscilloscope to measure this, but you know, all this is pretty simple. I worked at the National Magnet Lab at MIT for many years. The first national magnet lab for high magnetic field production was at MIT, and you would have an electromagnet, and often in physics you want to know what's happening, you know, to how do electrons behave in a sample, like a superconductor or something. So you want to put a high magnetic field on and just say measure the resistance. But the only way to do that would be to get a very high magnetic field. And so the National Magnetic Field Lab was made at MIT. So I did a lot of experiments over there. And when they initially operated in the 1960s, way before I got there, in their electromagnet, in their coil of wire, they used 10% of the power of electrical power of Cambridge in the early 1960s. So when they turned the magnet on, you'd be working on a little tiny piece of superconductor that you just invented, and took 10% of the electrical power of Cambridge. Okay. Anyways, the person who calibrated the magnetic field of these big magnets, electromagnets, used basically this, something like this. I mean, it wasn't a 741 chip, but it was an integrating apparatus. So he had basically a wooden pole, and he had a loop of wire on it, and hooked to an integrating circuit like this, and he would bring this coil down into the magnet, into the center of the magnetic solenoid. Anyway, so this is something that he actually calibrated the magnets, and people would come from all over the world just to use these magnets. Scientists would come in. Anyway, so this is a simplification of that. Okay, so you recall that this circuit here, the output is -1/r times C times the integral, right, of the voltage that goes in here. But the voltage that goes in from this coil, the EMF, is minus number of turn times the area times the rate of change of magnetic field. So here you see you have a formula for the output voltage, you have a formula for the input voltage. One is the integral and one's the derivative. Hey, put these two things together, I get rid of it. The integral of a derivative. And you're gonna integrate from infinity to inside the coil, basically. So you're gonna get a formula like this. So the output voltage is going to be equal to the change in magnetic field times some constants here. So you can measure this voltage change, the voltage change out here, as you bring this magnet into the coil. You can compute what the change in magnetic field is from how much voltage change you see. Any questions on this? I want to show you something. Hold on. Let's see. So if you want to make a magnetic coil, if you want to make a solenoid, you take you wind a whole bunch of wire around something, right, and put a huge current in of kiloamps or something. the problem is in a coil, there's a magnetic field acting on the current in the magnet, in the wire. And that's pushing, so if you have a coil of wire like this, there's a force pushing the wires out. And you reach a certain point where they push it out so much that they stretch and the insulation doesn't work, and then it shorts and it burns out. So there was a scientist, professor at MIT in the 1930s, Francis Bitter, who said, well, hey, let's change the shape of the wires. Let's make, instead of wires, have a round cross section, make them plates. So this is what's called a bitter plate. So this is just a wire that's squished. So the current's going to go around one of these things, and then you're going to hook another one to it, and then the wire is going to go around again and again and again. So they put insulators between these things so that one of these plates doesn't short out to the next one, and you have a whole stack of these things, and maybe the stack is nearly a foot tall. So that way you can clamp. They put stainless steel screws, basically bolts, that clamp this big thing together of all these turns, and it can withstand much higher radial forces trying to push this thing away and make it burn out. So then they got much higher fields, and now they can make about 30 Tesla with a magnet like this. So Francis Bitter in the 1930s developed these things. But I think his thinking was, hey, we don't have to have a round cross section for a wire. They can just be something like this. So this is a wire. The magnet lab has since moved to Florida, to Tallahassee. One of my friends is now the director down there. And they have fields to 45 Tesla, because they put a superconducting magnet around this to add the magnetic field. There are other ways to make large magnets that explode, and I can show you one here. So here's part of an exploding magnet. It's just two pieces like this, and one on top, one on the bottom, and then a little turn here, and then they put a whole lot of, they put a capacitor bank that's about the size of 3 or 4 SUVs charged up, and they discharge it across this, and produces a magnetic field by this half of 3/4 of a turn of copper, and that produces a magnetic field, but it turns into a plasma and it kind of explodes. But anyway, you get data in a few milliseconds. Okay, so that's it for today. We only lost a few students, so that's good. Anyway, so the experiment today, you're going to bring a magnet. You're gonna make this op-amp circuit with one coil, with a 100-turn coil. Bring the magnet in and out, and see its response, and you can actually get a value for the field of the magnet. And any closing questions? Okay. Okay, well, good luck this Thursday and Friday. Okay, that's all for now.
Actually, can you hold on? I actually have a question
Sure.
about.
Oh, yeah. You don't ask enough questions.
Yeah, sure. I have a question about the impedance.
Yeah. Okay.
So how does that actually, so I'm looking at it, and based on what you calculated, it seems to increase the current and drop the voltage. So how exactly, so the power output, what exactly would you get? Are you trying to increase current, or are you trying to increase voltage in order to match what you would normally get?
You're trying to get more power to it.
All right. So how exactly would you calculate the power going to it? It would just be like, because I think I calculated it and it was like 50 watts or something.
Huh. 50 watts.
If I was, because maybe I was just calculating it wrong and I was using the I probably was just calculating wrong. So you just you use just I squared R or V squared over R to calculate the power
Right.
to
Yeah.
confirm it. All right.
Well, whatever voltage you have on it, the resistance is fixed. So that means the current is fixed.
Yeah.
Yeah.
Yeah. All right. Thank you.
Yeah. Anybody else? Okay, remember we have two lectures next week, Monday and Wednesday. Okay, good luck. All right, bye.
Have a good day.
You too, yeah.
Thank you, Professor.
Thank you.